Ladies and gentlemen, I'm happy to welcome all of you here in this ancient cinema for a furthermore Swiss Nuclear Forum. Like usual in the last few years, the event is hybrid. That means you are present here physically, and of course we have also guests. They are watching the event on their screens. And one of our speakers tonight, Brian, happy welcome. He will also join us on the screen in a few minutes. Dear ladies and gentlemen, small modular reactors are on everyone's tips. Numerous countries are pushing the development of these new types of reactors. And not a week goes by without new milestones being announced, such as research collaborations, prototypes, or site decisions. As already mentioned, SMRs are a major topic of the Swiss Nuclear Forum this year. And not only the Swiss Nuclear Forum, but also the Nuclear Europe organization is very busy with this topic. We are therefore very pleased to present one of the most advanced projects to you today. That means the BWRX-300 is a 300 megawatt water-cooled natural circulation SMR with passive safety systems. The reactor is designed by GE-Hitachi Nuclear Energy. Many countries want to rely on SMR technology to push the decarbonization of their economies. Since nuclear energy is very climate friendly, this seems to be a very smart solution. It is also exciting that some countries are using SMR specifically to make their heavy industry climate friendly. In the future, electricity will simply be produced on the spot where it is consumed without the need for large grids. Who knows? Maybe one day there will be an SMR like the BWRX-300 in Switzerland. As we all know, hope dies last. Until then, unfortunately, we will probably have to be patient for a while. So let's start today by taking a close look on this type. And I'm happy to welcome here, first of all, Brian Box. He will start with the event. Brian Box, as an engineer with degrees from the University of Tennessee and from Wake Forest University in North Carolina, will introduce you to the design of the BWRX. And he is also the Vice President of GE-Hitachi Nuclear Energy, and he leads sales and commercial activities for advanced nuclear technologies. As I mentioned, Brian is joining us online from the United States, and as you can see, we have invited top-class speakers tonight who know what they are talking about. I'm also happy to welcome Christoph Gerber, an engineer who graduated at the Federal Institute of Technology in Zurich. He will show you the design of the steam turbine solution for the BWRX. And Christoph is leading the product management and global marketing team within GE, responsible for the global nuclear fleet. At the end, as usual, and last but not least, an instruction for our online participants. Please post your questions in the chat, and they will be discussed with the speakers afterwards. And now I'm happy to give the floor, the virtual floor, to Brian, and it's time of technology, and that's not my business. Thank you.
Hello, everyone. So good morning, afternoon from the United States. I apologize that I could not be in person, but I do appreciate the opportunity for us to talk about PWR X300 and the program. So for the past several decades, GE-Hitachi has been heavily involved with design, building, and servicing boiling water reactors around the country. There's over 65 reactors that are BWR, GE-Hitachi BWR technology that have been licensed around the world. So we've been focused primarily on the large reactors and the servicing of those across the country. But about 10 years ago, we noticed there was a shift in a lot of policies across the world for the reduction in carbon footprint and going to net zero, especially in the United States and Europe. So we had a team to take a look at how we might come up with a design that ended up being a small modular reactor that would have a better footprint across the world. And so what we came up with over the past several years is the BWR X300. And so today I'd like to just walk you through some of the attributes of the BWR X300 and also answer any questions that you may have. What you see on the screen is kind of the high level snapshot of BWR X300. It is 300 megawatts electric. The next few points on the page there, I'm going to cover on a few subsequent slides. So one of the things I'd like to touch on is the world-class safety. As with most Gen 3 plus reactors, the light water reactors, we do have world-class safety. One of the things I'd like to hit on first is the ability for walk-away safety without operator interaction. So we'll get into a little bit more of this later, but the BWR X300 as a minimum case can have 7 days walk-away safety so that no operator interaction has to happen to shut the reactor down. That's kind of what we based our safety case on. And that's kind of a worst case scenario. So we have triple redundancy for systems that will enable us to be more than 7 days, 7 days walk away, passive safety shutdown. The other thing we noticed too, with the shift of moving away from carbon sources of electricity, we wanted to make sure that this was sized appropriately for existing coal plants, because we do see a very close analogy between the size of 1 or 2 or 3 of the units paired up nicely with an existing coal facility and the existing infrastructure there fits nicely. So if you take a look, you've convinced yourself that small modular reactors are definitely part of the energy landscape across the world. Why would you look at BWR X300? I think there's several reasons that I'd like to focus on here that I think make it very attractive product and where we're seeing a lot of progress across the country or across the world. We're on our 10th generation boiling water reactor. So the X300 is the 10th generation. We've been at this for over 60 years, building reactors, helping utilities operate reactors, also doing the refueling outages and servicing of reactors, and also making significant improvements over time, not only for safety for the existing fleet, but also to improve operation, reduce outage duration, and therefore reducing your operating costs across the fleet. The BWR X300 is also based on an existing licensed design, the ESBWR, which is one of the first units that we have eliminated a lot of the jet pumps and other things that drive the reaction. And now we're based on natural circulation. So by doing that, that has made this an inherently simple to operate machine versus some of the prior generations. One of the most important points that I think you could take away from today too is we are already manufacturing and using the fuel across the BWR fleet for the exact same fuel that's going to go into the BWR X300. The GNF2 fuel's been produced over 25,000 bundles and has been used across the world. So we kind of have a leg up or a lead on any other technology that has to develop fuel. Generally, it takes about 10 years from the time that you introduce a new fuel type and get it qualified through your regulator in your country. So this has been being manufactured for over 20 years, and like I said, we have over 25,000 bundles in service. So we're very confident this fuel is going to fit this footprint very nicely. So the design is exactly the same. A couple other things too that help us drive costs down for this reactor. When you base a reactor on a larger technology and then you're scaling down, you do have to get very creative and innovative to be able to have the economies of scale work in your favor. One of the first things we did was we looked at the current design and how we can improve it. And the key innovation that drives this is the integral isolation valve. So simply put, it's basically a valve that's attached directly to the reactor pressure vessel, and thereby eliminating the ability for a loss of coolant accident to happen. So basically a large break FOCA would occur in one of the pipes between the reactor pressure vessel and the first set of valves. And by doing that, now you have to have redundant systems to make up the inventory that's lost in the reactor pressure vessel. By eliminating this through creating this integral isolation valve, which is now part of the reactor pressure vessel, we now can simplify the entire system and eliminate a lot of the redundant pools of water that have to happen to operate the safety system. So by doing that, we have significantly reduced the footprint per megawatt, which then drives down less concrete, less steel, less construction costs, as well as makes this a much simpler unit to operate. So we expect to have a much shorter outage duration, where we take a third of the fuel out and do the refueling, as well as just normal operations. There's less equipment to operate and less equipment to have to maintain. One of the other things too that we take advantage of in our supply chain is the use of the existing supply chain, because like I said before, not only are we already making the fuel the exact fuel that's going to go in, but also this reactor being based on a prior generation, some of the reactor internals like steam dryers, steam separators, some of the other configurations that are inside this plant, we already have the existing supply chain that has manufactured and services these components today. So we're going to be tapping into that existing supply chain to scale with us, and should prove our ability to build a large fleet of reactors across the world. The other thing too I'd like to touch on is not only is this reactor going to be deployed for the typical electricity utility model, but also there's a lot of interest across the world due to this size of replacing the coal footprint for district heating, and then also some of the other things you can see on the bottom of the page. The hydrogen economy, this fits very nicely, this footprint with hydrogen production, and then some of the other downstream things such as synthetic aviation fuel, et cetera. Kind of touched on this before, but why GE or why GE-Hitachi? Like I said, we've been at this for quite a while. We've been at this over 60 years in the nuclear space. In fact, we had the first reactor that was commercially owned. That was in Canada. We like to say we're coming full circle. I'll touch on our activities in Canada in just a second, but I'm sure most people in the audience are aware we're going to be deploying the BWRX-300 in Canada with Ontario Power Generation. So we like to say we're coming full circle with the first reactor happening in Canada back in the 60s, and then now we're looking at deploying in the late 2020s our first reactor at the Darlington facility, Darlington site. I'd already mentioned too that we have 67 reactors licensed in 10 countries. There's still dozen in operation. I think it's about 23, 24 in the US alone. So when you think about a company that has not only the technology that's evolved over time and on its 10th generation, you also have a company that has decades of experience servicing reactors. So I think that kind of puts us in a unique position of a lot of folks that are looking to deploy, where we fully understand how to take a reactor apart, how to refuel the reactor, how to do inspections, how to do a lot of the modifications that may need to happen over time, and then also get the reactor back online as quickly as possible, which is one of the most important things, because the less time you're down, the more electricity, or the more you're able to generate steam to produce some of these downstream products. We also mentioned the bundles of fuel. The last thing I kind of like to touch on is we're in deployment mode. I think the best way we can put this is not something that's a demonstration project. This is not something that we're doing the design and looking forward in the future for deployment. We're already active contracts in execution mode. And as I've mentioned in the upper left, with Canada, Ontario Power Generation is looking to complete their construction in 2028, commercial operation starting in 2029. So it's pretty exciting. Before the end of this decade, we do expect one, if not more, to be online, operating, generating safe, clean, reliable electricity to the grid in Canada, which should set up, as well as the industry, very nicely for more SMRs to come online. And as confidence builds, we expect this to scale accordingly. So some of the activities that's happened in Canada, OPG's already submitted their construction license. So we're already actively working with the CNSC in Canada through OPG to get this license approved so that they can move forward with the large scale construction. Also in Canada, we've been selected by SAS Power. I was actually there yesterday with the SAS Power team. That's one of the reasons I couldn't be with you today. And they're looking at potential deployment in Saskatchewan as well. With a lot of the coal retirements and the aggressive carbon goals that Canada has, they're looking to use the BWRX-300 to meet some of the goals. As we look across Europe, Poland is really where we have a lot of our activity. We have partners there, not only partnering with us on our standard design development and deployment, but also looking to build a significant fleet of reactors. As you're full well aware, Europe has the added energy security criteria on top of just looking toward carbon footprint goals. So we're moving very quickly in Europe, starting in Poland, and also in looking in other places in Europe to deploy these reactors. Poland is very serious about deploying quickly, not only to replace a lot of their coal fleet and to end the reliance that they have on Russian supply. In the U.S., our lead customer, or our first unit that we're looking to deploy, we're working with Tennessee Valley Authority, the TVA in the Tennessee area, to deploy at the Clinch River site. TVA is a current customer of ours. They have BWRs operating today. We do a lot of the servicing and fuels of those, so we have a really good relationship with the Valley Authority, and we're just looking to build on top of that. So we're working through TVA with the U.S. Nuclear Regulatory Commission to look at how to permit the site, how to move forward. So a lot of exciting things going on. So you can see just there alone that four customers, utility scale, that are looking to deploy not just one, but also looking at how they can deploy a fleet of BWRX-300s, which should just provide lift in those countries for the second, third. For the rest of the world, we have agreements in place in the Czech Republic. We have contracts with Firma Energia in Estonia to look at developing there. And then there's active discussions across the world. But you can see just by focusing on the US, Europe, and Canada alone, there's a tremendous amount of activity. And we do believe these three regions will be leading the world on deploying not only our technology, but also other technologies as well. So that's the end of my prepared remarks. I really appreciate you guys giving me an opportunity to come in and talk about X300. And I will stay on the phone for questions at the end. Thank you.
Good, you can hear me, perfect. Good evening, and thanks for giving me the opportunity actually to talk about this, oh yeah, different name. Give me the opportunity to talk about the very exciting topic about the small modular reactor. While Brian, our colleague from GE-Hitachi, was talking and covering the reactor, in particular, I will give some insights now on the next slide, more on the steam turbine side. I will talk about our strategy and our design solution for the BWRX-300, but not only, I will also give a bit an outlook of our global strategy that we are following in GE to address and be part of the, as we believe, emerging market of the SMRs. Good, so I will actually start with a small outlook about the SMR market, how we see the long-term development of that area. Then I will show you the portfolio and our strategy that we are following to develop the right solutions for that topic. And in the end, I will give some details on some of the key features and success factors that we believe are relevant for the steam turbine design for SMRs. We believe there are three main contributors to the SMR market scenario that we are seeing. First of all, we all know the global energy generation will grow significantly in the coming years. 50% or even more by 2040. You see on the graph on the right-hand side the expected growth by 2030 in the order of 25% and a similar amount again by 2040. Renewables, including hydro, are obviously growing, expected to grow significantly, but by no means this will be sufficient to fully cover the electricity needs. And if we have a bit more detailed look at the graph on the right-hand side, we all know coal is going down, will reduce, gas probably similarly, a bit later we expect, while renewable is significantly growing, which means there is still a big need for nuclear generation. Percentage-wise, the shares remain about the same, but due to the absolute increase, we have a significant need of additional generation from nukes by 2030 and 2040. And the third element, obviously, is the decarbonization strategy and what that means for the SMR specifically in the short term as part of the SMR strategy 3040. We expect that SMRs will replace some of the decommissioned fossil fuels. That's also why this, for instance, because why the size of the BWRX-300 we believe is chosen in the 300 megawatt range, because a majority of the fossil fuels that are decommissioned are in that power output range. While in the longer term the situation is unclear. It will be an interaction, we believe, between small and large reactors, and also depends on the future hydrogen situation, as also shown by Brian. SMRs will be a contributor to hydrogen generation, so there are many influencing factors. We have to see how that develops in the very long term. We made a little math to look at global nuclear generation on the bottom left. So the install base last year or the year before was about 400 gigawatt. By 2040, we expect generation in the order of 700 gigawatt. When we add also expected decommissioning in the order of 6 gigawatt per year. We see a global nuclear capacity addition per year of 20 gigawatt. This will be back-end loaded, we believe, and in the end, this will be covered by a mix again of large and small reactors. This page actually shows a list of reactor developers, and it's important for us, and also that's what I want to share. We are not focusing on BWRX 300 only. So we have a global strategy. We want to cover a wide range of reactor developers. And we want to cover what you see on the top of the page, reactor developers or reactors that are generating moderate steam conditions, but also, and that's an even longer term play, reactors that will provide advanced steam conditions. You see, I mean, this shortlist has been generated based on a number of criteria. In total, across the world, there are more than 90 reactor developers trying to contribute to that market. So we have screened that list and defined criteria based on which we define the shortlist of reactor developers that we want to focus on. Obviously, GE-Hitachi with BWRX 300 is one of the key reactor developers that we are following. Good. On this page, you see our steam turbine portfolio for the complete nuclear fleet. On the top, the well-known Arabelle design for the large and very large reactors, covering a range of 700 up to 1.9 gigawatt, 700 megawatt up to 1.9 gigawatt. While on the lower part of the table, that's our planned portfolio, how we want to cover the reactor for small modular reactors for a range above 50 megawatt. So if we look at the N100, so the smallest solutions, that's a range for 50 up to 130 megawatt. A typical example is NuScale. I think most of you have heard of these activities. It's a single shaft turbine which provides power output in the order of 70 megawatt. The N200 frame covers a range between 100 and 350 megawatt. It can be configured with 1 LP or 2 LPs, depending the size and the volume flow in the end that needs to be covered. An example would be for the smaller size, the new watt opportunity, which is being developed by EDF, and on the bigger end of that range would be the BWRX 300, as we know, in the order of 300 plus megawatt power output, which considers 2 LPs at the end of the HP turbine. STF N400, a range between 250 and 500 megawatt. An example here would be the Rolls-Royce solution. And then at the end of the range, for instance, the Westinghouse application, which is the N700 frame, which is an application for advanced steam condition, which will come even later than the conventional steam conditioned reactors. Some key factors that we believe are critical for the success of the SMR journey. Cost, obviously, is one of the key elements. We are designing our solution for cost. We are optimizing our turbine and the generator specifically to reduce cost as much as possible, looking at all the aspects, at the design, at the configuration, at the material. At the same time, we also improve performance as good as possible. So we need to find the right balance to drive down cost, but also have a high-performing steam turbine. And at the same time, because we talk nuclear, obviously we need to make sure that the design is resistant against wetness. We are also looking at the sourcing and supply chain, again, to reduce costs, but also to improve lead time, which is a key element of the SMRs compared to the large nukes, as we know. And we want to develop a standard product portfolio which again helps to reduce costs, which helps to improve lead time, and this standardization that should really cover the complete target range between 50 and 500 megawatt. Modularization, as per the name, we are looking into that, trying to assess if this impacts for our scope lead time, transportation costs. It will improve quality because we have a bigger scope in-house our workshops in terms of assembly. And it would also give an advantage of the accuracy of the planning, the schedule, and the costing, again, because of less uncertainty during site erection. And last but not least, we are also trying to optimize our execution process, again, for minimizing execution time and also execution cost in the end. Some details on the specifics of the BWRX-300, or the steam turbine of the BWRX-300. So you see on the right-hand side, as mentioned, it's a solution with an HP and 2 LPs. You also see the MSR in yellow. I don't want to go through each and every details. What I would like to emphasize on this slide is the ability to cover a wide range of applications. So we expect and we want to cover 50 Hertz and 60 Hertz applications. You have seen from the slide from Brian that the target is US with 60 Hertz, but also Europe, in Poland, for instance, with 50 Hertz. And obviously, depending, again, the site, there will be different cooling conditions, which has an impact on the detailed steam path design. But all this should not change the footprint, the outer shape of our solution. So from outside, you will not see a difference. But in the end, we can accommodate those changes by optimizing the steam path, mainly by exchanging, for instance, the rear stages, the last stage blades in the LPs, to have optimized operation and also properly coverage of the related back pressure condition. We also have the opportunity to consider monoblock or welded rotor design, which is a big advantage in terms of reducing and mitigating the risk of stress corrosion cracking, but also minimizing the inspection efforts and durations if we talk about welded rotor. So depending the requirements coming from the customer, we can choose and select the appropriate design there. Again, to go a bit into the key features, modularization, compactness is a key aspect in our view because the advantages we see in terms of transportation costs that will reduce shorter erection time, less site labor cost, and reduce quality risks. And all this mainly driven by the pre-assembly we can consider in our own factories. Our blading technology, obviously optimized designs with high-strength steel where appropriate and required. We have LSBs with damping technologies. So on the left-hand side, you see a picture here of an LSB that has a connecting element which has some loose parts in between that helps to damp the blade in terms of excitation, so that if vibration occurs, it automatically gets damped away. Four-hook root design for optimized stress distribution. And obviously as high as possible efficiency using the state-of-the-art 3D profiles for our all our blading, standard and LSB blading. As mentioned, rotor and bearing design, we have a single bearing concept between turbines and the generators, helping to reduce again the footprint, which is a key factor, and also improving the installation and alignment requirements. And as mentioned before, the welded rotor helps to select the materials ideally and improves inspection and resistance against SCC. That's my last slide. I just wanted to give a quick outlook about one of the key components, which is the LSB. which is always treated as one of the high-risk items, so needs to be treated with special caution. And you see on the right-hand side our portfolio, which is a key driver actually to really cover the ranges we need to cover. So depending the power output and the back pressure of the specific applications, we choose the right blade. Is it a double connected rigid connection at the upper end of the range? Is it a freestanding blade? Is it a single connected damped blade? And each of those blades are optimized to the extent possible with our standard 3D CFD tools to provide performance as good as possible. Inspection intervals apply here for 100,000 equivalent operating hours, which is also a key element. And we have a lot of references for those designs. So it's proven technology, it's proven design features, which is important specifically in the nuclear field of application. Good, I stop here. I think questions will be covered separately. Thank you for your attention.
You can. Yeah, dear Christoph, dear Brian, dear friends of the Swiss Nuclear Forum, I would like to thank you both for the very exciting presentations. I was deeply impressed about your progress. And once again, I think we have learned a lot here in the room. And personally, I would like to start an SMR project in Switzerland right away, so it should not fail because of us here in the room. Are there any questions? Yes, please. Hi, you. We have a microphone for you so that Brian can hear us.
Yeah. Is this turbine plant designed for load following operation or is it for base load?
We can cover both. I mean, the main requirement is base load, but we know that more and more in the nuclear area, changing or part load and in particular different speed gradients in running up and down are getting more relevant. And this might also be a key trigger for the SMR. So that's an aspect we are considering, to be able to operate at part load and also cover change in speed for regular run up and run down, which is a difference compared to the past for the large nukes, which typically are base load driven.
Another question about the reactor. In Switzerland, we had 2 BWR reactors, and the problem there is that they cannot be operated in natural circulation because the void feedback can agitate oscillations in reactivity and in power. So there's always a minimum recirculation needed. How do you solve this problem with this reactor, which has no circulation system?
If that question was to me, I wasn't able to hear the whole question. Is there a way to repeat it, please?
Ja, ich glaube, du musst sie noch einmal stellen.
Okay, BWR reactors tend to oscillations due to feedback of void fraction to reactivity, and they cannot be operated in natural circulations. And my question is, how do you solve this problem in the BWRX?
I apologize. I missed the first sentence. There's a little noise in the back and it cut off.
Okay, that's a pity. So I think we will ask a question by email. That's okay. Possible after. So.
Okay,
yeah,
thank you.
Fine. I apologize.
Yeah, that's no problem.
We're having connection problems. I'd be happy to answer anything via email if we can't connect to work.
Okay. Are there any other questions?
Thank you. The BWRX 300, is that going to be one standard design which is basically licensed with a type approval which can, if possible, be used internationally? Because I think one of the main problems of the industry now is that every country has its own regulation, its own requirements, which drives building costs up and makes building difficult and long-winded. How will it be with the BWRX 300?
So thank you for the question. I wasn't able to hear that one. Yes, our goal is definitely to have one standard design that we base all of the licensing for each country on. I agree with you. Traditionally, it's happened not only across the world but also in the United States. There's been a lot of different reactor designs that have evolved, and a lot of different reactors that aren't the same, even some that sit on the same site, and that does drive operating cost up. It does drive obsolescence issues. It drives a lot of things downstream that can, really be a deterrent. So we're driving really hard to have a standard design. We believe we can accommodate the different licensing paths, not only in Poland, Canada, and the U.S., with one standard design. So we are driving toward that and do expect to be able to in that. Also, just the fact that the reactor is much, much simpler. There's a lot less component configurations that we're going to need to worry about. So we feel very confident that we're going to be able to achieve that with the X300. Thank you for your question.
Yeah, just wanted to ask for the other technologies that you are for the other SMR you are following for turbine design. How did you come up with the list? Are these just the most likely clients you're going to have, or you think that those are the other SMR that are more likely to be built?
In the end, it drives down to our expectation of the likelihood that they will make the race in the end. So there is a number of criteria. One, for instance, is our assessment of the technology maturity of the different companies. And as you may remember on the list, we have like a top 4. GE-Hitachi, BWRX 300 is one of it. Rolls-Royce is quite advanced as well, which is another one. And Nukleare from EDF is a third one, where we think they are quite mature and have quite a solid plan already. So that's the main trigger for us to focus on those. Yes.
I have a question regarding the steam turbine, and mainly the size of the steam turbine. Was there no option to design the entire plant in such a range that you can have an axial exhaust of the steam turbine? I mean, we heard quite a lot about cost optimization and so on. And I mean, if you have a steam table, yes or not, that of course can save a lot of costs.
We have looked into that, and again, the reasoning to select for one design, we have a sideward exhaust. For others, it's downward. Yeah, in the end, it's you need to understand the best solution in terms of performance, cost, footprint. And in the end, it would be possible. So it would be possible to have an axial exhaust, but based on our assessment criteria, it wouldn't make sense.
What would be the size, the total power output size, if you have an axial exhaust of the steam turbine?
I would have to check that one, but maybe we can follow up afterwards to go into the details.
Okay.
I have one question for Brian and one for Christoph, if I may. So I'll start with Brian. So at the beginning of your presentation, you were saying that you started the design process for the BWRX by looking at what you can improve on the existing BWR design. And I was wondering, have you considered how you can improve also the decommissioning of those reactors directly as part of the design?
Was the question on the decommissioning? Was that what you said?
Yes, if decommissioning was considered as part of the design already.
Yeah, absolutely. We do look at decommissioning as part of the design. And I think in general, you could say that commissioning of a smaller unit with fewer components, less structures that you're going to have to decommission should play into that being a much lower cost. But, also looking at hopefully having these reactors run 80 to 100 years as well. So we'll be looking at planning that at that point too. We take advantage of some of the opportunities and some of the things that we're doing right now with some of the decommissioning and taking the learn to move forward.
Okay, thank you. And my question for Christoph is that, so normally when we talk about small modular reactors, one of the arguments for why they will be cheaper or easier to build is that you can use a lot of off-the-shelf parts. And here we're talking about designing basically a custom turbine still from a nuclear vendor coming from more the nuclear side. And even though you're trying to push the costs down, I imagine there is a lot of competition in the established non-nuclear markets for these turbines. Could you perhaps comment, are you cost competitive also with the non-nuclear sector, or do you offer some added value that they don't?
I'm not sure I fully understand the question. What I can say is that parts of our design are actually based on our experience and also on what we are deploying for the fossil fleet that way as part of GE. So we take the benefit from the experience we have in the fossil fleet and apply it on the SMRs, taking into consideration the nuclearization that is required. There are obviously some aspects that need to be adapted for wetness, for corrosion is a big topic. But one of the big benefits is that we can adapt or adopt from the existing experience in the fossil fleet, where also there obviously cost is a key element, was always a key element. And yes, I think we have a cost competitive product also for fossil applications.
Thank you.
Okay, I've got a question from the online chat from Franz Liebermann. He's asking, how many years are we away from a nuclear power station built in a standard container as promoted, e.g. by X Energy? Don't know I think it's for Brian, huh? Should I repeat?
So I heard the first part of the question. How many years away are we
from a nuclear power station built in a standard container, as promoted, e.g. by X Energy?
Oh, in a standard container?
Yes.
I can answer kind of from what our perspective is on modularization, and I think that's something that we are driving towards to deploy. We deploy it as a large fleet. We haven't contemplated standard container where it's fully assembled. We believe that there's advantage that you can do off-site with putting together modules and assembling those on-site, but we're not looking to drive toward a single container. You open the box and drop the reactor in. That might be applicable for small sizes, but for us, we do see advantages in modular design. Some things being manufactured off-site and connected on-site, but that's not part of our current configuration.
There have been quite a few questions and remarks about cost efficiency, and so on. So we have seen the last plants that have been built in the US, Vogtle, here in Europe, Flamanville, Olkiluoto, where cost has basically gone through the roof during construction. We can probably expect that the first 2 or 3 BWRXs, which are 300, which will be built, there'll be some learning curve. What do you expect compared to the cost of the large units nowadays will be sort of the N+1 cost once the manufacturing of the BWR X300 has taken up and going on. Don't give me an absolute number or I'll sign the contract today, but give me sort of a comparison compared to today's units, where we should land with these units.
So I can say, thank you for your question. I was able to hear okay. I can say we do expect the subsequent units to come down the cost curve considerably after the first time. Some of the areas that I think we're going to be able to take advantage of, which should drive costs down, are our construction technique. I think sounds like pretty familiar. The typical construction technique is similar. We could refer to subconstruction, where you're going out meters outside of and having to remove earth and come in and backfill with your engineered backfill. By eliminating that, that's cost down, but able to use what we're calling thinking technique, much more economical and much quicker way to dig the hole, so to speak. Also, by the earlier question, if I have modules come in and then be assembled versus what we would say stick built on site, that should drive it. But it's a lot about duration and how many people are going to have on site at a time. So we see advantages of those coming as we deploy as a fleet.
Oh yeah, please.
Follow-up question on the first question that you couldn't hear very well. So the question was on thermal hydraulic instabilities due to natural circulation in combination with the kinetics of the core. So how did you sort them out? Because in our BWR6 and BWR4, we needed forced circulation. Thank you.
So just general, without going too deep into the engineering, physics, and some of those, at a top level, this reactor controlled by moving the rods. That's going to be how you control the reaction. That's probably as far as we can go. To go much deeper into thermal fatigue, thermal hydraulic analysis, we have a discussion. This unit is operated moving the rod to control the reactor.
Are there any other questions? No? So maybe a last question? Yes? Oh, yes, please. Okay.
Hi. Hope you can hear me, but just to go back to the cost matter. I mean, you've got a construction has, in a way, started, or site preparation in Canada. It looks like it's going to be 4 units. What's the cost for that? Do you have a number?
It's not something I can publicly disclose.
Okay.
Thanks for the question. I really appreciate the interest.
It's just in Switzerland. We won't tell anyone.
Thank you.
Thanks.
Okay, other questions? So, Brian, I have a question. Do you hear me?
I can, yes.
Ah, wonderful. Okay. So, in short, why is your SMR better than the other projects?
Yeah, I think there's several reasons. Some of those that I touched on. The first thing is the experience that we have not only in designing reactors that have been built and are still operating and are going through their second life of license extension to operate more than 60 years. So we know we have confidence that we know how to design reactors that can be built and operated. One of the other things that you can feel very confident too is our ability to manufacture fuel that is in operation today. I think I misstated earlier, it's over 165,000 bundles of DNF2 that are in service today. So you should have confidence that the fuel, we know how to make the fuel work, we know how to design the core. Some of the other things too is we know how to service this reactor. So not only do we're able to start them up, but we're able to take them on and do the refueling and to make sure that they can offer long duration. Some of the other benefits you get too is we already know the supply chain that exists because they're operating today. I could go on and on, but I think those are some of the key things that, that put Hitachi ahead of others. And then also the last thing I would say specific to X300 is have a commercial project that we're working on and we're going to deploy. And we have others that'll be followers and a lot of other interest with utility scale. So we feel really confident and very excited about the future. I think in general, everyone should feel very excited about nuclear because it's a different perspective than what we would have looked at even 3 years ago, 4 years ago. Here, it's now, it's happening. We're going to have a very big impact, not only on energy security in Europe, but also on decarbonization of the world, meet everyone's goals. So I appreciate the opportunity to talk to you guys. I think we're well positioned, and we're pretty excited about what's going on at GE for new and advanced.
So thank you very much. We look forward to it. Of course, we have presents for you. For Christoph, who is here in Switzerland, we have a bottle of wine for you.
Thank you.
And I will give it to you after. And for Brian, it's a bit difficult at the moment to send wine to the United States. So what we did, we sent you typical Swiss sweets. It's called Basler Leckerli. I hope you will like it. So a warm applause for the... So I would also...
Thank you. Since it's being shipped to my house, I'll have to make sure that I get to the mailbox before my daughter does. Yeah. Thank you very much.
Yeah, you should get them tomorrow, I think. Okay.
I'll be on the lookout. Thank you.
Okay. Thank you. I would also like to thank Robert Faltermeier and his team at GE for the support. And with this event, the Swiss Nuclear Forum goes into summer break. But don't worry, we are back in August. As you might know, there are parliamentary elections in Switzerland in October, and we will invite numerous candidates to the forum and ask them what they think about nuclear energy. So you can look forward to vibrant debates, and I hope you will join the discussions. I mean, basically, nuclear energy in Switzerland needs your support more than ever. And in November, we will show the new film Nuclear Now by Oliver Stone. So then we will once again be here in a cinema. I hope to see many of you again. So last but not least, I wish you all a wonderful summertime, and I hope to see you all outside at the apéro. So enjoy it. Cheers.